Welcome to this explainer. Today, we are unpacking Section 3 of the ASNS 3000-2018 wiring rules. Now, look, if you've ever stared at a massive, dense electrical regulatory manual and felt your eyes immediately glaze over, you know what? You were definitely not alone. But today, we're going to translate that dense regulatory text into a visual journey of safety and compliance. We're focusing specifically on the selection and installation of wiring systems. Think of it as an environmental odyssey, tracing the exact path our electrical cables take through the various extreme environments they have to survive to keep our buildings powered and, most importantly, our people safe. It's a serious question, right? Because before we jump into the rules themselves, it's absolutely crucial to understand that these standards aren't just arbitrary red tape designed to make your life harder. They're highly engineered solutions to the very real physical hazards of electricity. An electrical installation literally has to protect persons, livestock, and property from harmful effects. It has to function perfectly, and it must withstand mechanical, environmental, and external influences. If a wire fails, the results can be catastrophic, so the code exists to ensure that a simple wire remains a helpful tool rather than turning into a deadly hazard. To see exactly how this is achieved, we're going to follow a single wire on this environmental odyssey. We'll hit 5 main stages today: choosing the right cable, managing voltage and heat, safely enclosing the wiring, underground wiring system rules, and finally, aerial wiring and clearances. Okay, let's dive straight into our first section: choosing the right cable, and specifically, current capacity. It all begins with one core concept: current carrying capacity. The code dictates that every single conductor must have a capacity not less than the current it's meant to carry. Makes sense, right? But here's the catch. It's not just about the load right this second. You have to anticipate reasonably foreseeable changes to external influences. For example, say you are wiring a domestic installation. Well, the standard requires you to assume that bulk thermal insulation in the ceilings, walls, or under floors is going to be installed in the future, even if it's not there today. And let me tell you, that changes the thermal dynamics of your cable entirely. Just look at how the material of the cable dictates its limits. A standard thermoplastic V75 cable maxes out at 75 degrees Celsius. But if you upgrade to a cross-linked polyethylene X90 cable, it can safely operate all the way up to 90 degrees. This is exactly why external influences, like being totally surrounded by that future bulk thermal insulation we just talked about, radically change the math on a cable's capacity. Heat has to dissipate. If it can't, the cable's internal temperature spikes and you start degrading the insulation. That naturally leads us right into Section 2, managing voltage and heat, focusing on voltage drop limits. As current travels through a conductor, it naturally encounters resistance, and that causes a drop in voltage. Think of voltage drop kind of like water pressure losing its force over a really, really long pipe. If a cable run is too long, or maybe the wire is just too thin, the equipment at the end of the line simply won't get the electrical pressure, the voltage, it needs to safely and correctly function. The standard is super clear here. The voltage at the terminals of any power-consuming equipment must not fall below the lower limit specified in its relevant equipment standard. And the crucial threshold for that is 5%. To prevent equipment failure, the standard mandates a strict rule. The maximum allowable voltage drop from the supply point to anywhere in the installation absolutely cannot exceed 5% of the nominal voltage. Now, actually, there are a few tiny exceptions, like if your supply point is a dedicated substation on the premises, you might be allowed 7%, but for the vast majority of installations, 5% is the hard limit that dictates your minimum conductor size for those long runs. Let's keep moving outward to Section 3, safely enclosing the wiring for mechanical protection. This is a really fundamental installation rule. The outer sheath of a cable actually dictates whether or not you must provide additional mechanical protection, like conduit, for indoor environments. So if you're using insulated unsheathed cables, the code says they must be enclosed in a wiring enclosure, like a conduit or cable trunking, throughout their entire length, no exceptions. But if you are using insulated and sheath cables, they generally don't need to be installed in an enclosure because that outer sheath itself is already providing that baseline layer of protection against the elements and minor mechanical wear. But what happens when our wiring enclosure has to pass through a fire-rated barrier? Well, you have to stop the wiring from becoming a fire highway. And doing that requires 3 critical steps. First, you need an internal seal inside the conduit. Second, you need an external seal around it to fully reinstate the wall's original fire rating. And third, crucially, you have to do a material check to ensure all those seals permit thermal movement and won't just fail under the extreme stress of a fire. All right, let's step completely outside the building now for Section 4, Underground wiring system rules. Taking our cable outside and burying it in the earth requires a whole new set of minimum safety parameters. The standard actually classifies underground wiring into 3 specific categories, entirely determined by the type of cable and the form of enclosure you're using. Category A gives you the highest intrinsic mechanical protection. We're talking cables enclosed in heavy-duty conduit or galvanized steel pipe. Category B systems might use a medium-duty conduit, but they require extra mechanical protection layered over them, like a polymeric table cover strip. And finally, Category C is for very specific environments, where your cables are chased directly into rock and then covered with concrete. Because these cables are completely out of sight, depth becomes your primary defense. And this number right here is absolutely critical: 500 millimeters. That is the minimum depth of cover required for Category A and B systems when they are buried under natural ground with no surface covering. Why exactly 500 millimeters? Well, because that's the depth calculated to stop a rogue manual digger or an overly enthusiastic operator in a mechanical excavator from causing a fatal strike before they realize something is down there. However, context is everything in the wiring rules. If that exact same wire is running directly beneath continuous poured concrete, specifically concrete of at least 75 millimeters thickness, within the confines of a building, that minimum depth drops to just 75 millimeters. Because the concrete slab itself serves as this impenetrable physical barrier to accidental excavation, the standard allows the cable to safely sit much closer to the surface. But listen, depth alone just isn't enough. We need visual warnings too. Orange marker tape must be strategically placed at approximately 50% of the depth of cover right above the wiring. Think about it. If a backhoe starts digging, they're going to hit that highly visible orange tape halfway down, and it's basically screaming at them to stop immediately before they hit live cables. Oh, and for Category C, since it's chased in rock, that tape just goes directly on top of where the concrete is poured in. Finally, for our 5th section, let's look up to the sky: aerial wiring and clearances. Above-ground wiring presents entirely different hazards: wind, tension, and accidental contact from elevated areas. Aerial conductors are strung between poles or structures, which means they're carrying their own weight and getting absolutely battered by wind. Because they're subject to immense physical tension and swaying, the code explicitly prohibits making joints in certain types of cables while they are in tension. You just cannot make a joint in parallel-webbed or multi-core cables that are taking that physical strain. And crucially, any connections or joints in aerial conductors in tension must be made without soldering. Solder suffers from creep and mechanical stress over time. A soldered joint swinging in the breeze? Yeah, that is literally a failure waiting to happen. When it comes to aerial clearances, distance is safety. Bare wires are a massive hazard near structures, which is exactly why the code strictly dictates insulation whenever the wire comes within arm's reach of a building opening, or a structure. It's all about protecting everyday people. If someone leans out a window or stands on a balcony, the rules ensure they cannot accidentally touch a live, bare overhead conductor. And that brings us to the end of our environmental odyssey. By mastering Section 3 of the wiring rules, you ensure that no matter where your wire travels, whether it's generating heat inside a fire-rated wall, buried deep under the earth beneath orange warning tape, or swaying in the air high above a roof, it remains a safe, highly engineered, and strictly compliant solution. So I'll leave you with this thought. Knowing the intense physics and environmental demands placed on every single circuit we build, will your next installation stand the test of the elements? Thank you so much for joining me on this explainer. Keep learning, stay safe, and I'll catch you next time.